degenerative because it's degeneration of the nerve cells. Now, surrounding the nerve cells, and in fact the more dominant cell in the brain, are these glial cells. And these sort of support nerve cells and have a number of functions. And many people say that these are the most important cells in the brain. Einstein was said to have more glial cells than the average person. So that might be why he had some of his great thoughts. But the role of glial cells in these diseases is unclear. They certainly react to lost cells. They may even be contributing to it. And more recently, it's become quite clear that inflammation within the brain itself accumulates around the site of nerve loss and where things die off. And the question has always been, is that inflammation simply the consequence because everything's dying off and you need to clear it, or is it actually that the inflammation is causing some of the nerve cells to die off? And that has therapeutic implications because obviously if we target these three areas, what can we do to arrest this process or repair it? I'm not going to talk about how we get into the biology of the disease and stop it. How can we repair the brain that's in trouble? Well, essentially there are three ways to do this. One is you can give fertilizer, so you can give growth factors to try and promote the growth of the cells that are there. So the idea here is you don't stop the nerve loss in the sense that you can prevent it, but those that are there, you try and rescue them and you try and get them to perform better. You can take the simple approach that the cells have gone, so let's just replace them. So transplant things into the brain, and that's a pretty hot area at the moment, and I'll talk about that. And then obviously if inflammation is a critical factor, so inflammation is driving the disease in some way, then give drugs that stop inflammation. And that obviously is quite intuitively attractive because the first two sound a bit complicated, giving some fertilizer to the brain, sticking some cells in the brain. But giving drugs that stop inflammation, probably half the audience are taking drugs that stop inflammation. So there is a question about whether this is an area that we could actually do more about now. But I'm not going to talk about that. I'm really going to talk about these first two areas. So I'm going to do this in the context of Parkinson's disease. And this is named after James Parkinson, who wrote an essay on the shaking palsy in 1817. So 200 years ago, James Parkinson wrote his famous essay. It was based on 6 patients. I think only 2 of them were his own patients. The other 4 were people he saw walking around the East End of London. And I had this great pleasure of talking at one of the anniversary meetings of James Parkinson in London. And I was asked if I would like to go to James Parkinson's house in Hoxton Square for dinner. And I said that would be very, very much like to do. It's a great honour to go to James Parkinson's house. So I did go to dinner at James Parkinson's house, and you'll be pleased to know it's a Bill's, and any one of you can go for dinner at James Parkinson's house. So having especially gone round for this dinner, I'm slightly disappointed that there's no great privilege for going. But what is Parkinson's disease? So Parkinson's disease is classically defined, and although people have changed the name, it's not quite as simple as this. This is still the common features of it. So essentially you have a resting tremor, you have some slowness of movement, some stiffness of the muscles, and a tendency to fall. So that is clinically how it's defined, and even in 2017, the diagnosis is made by someone saying they've got Parkinson's disease. There's no diagnostic test, but in the right hands, following people for a few years, you're right about 99 times out of 100. And this is a condition that affects about 128,000 people in the UK. So does anyone know this week someone who was one of my great heroes, not that you'd know that, who died of Parkinson's disease? Brian Kent. What a genius. So I don't know, I'll probably show my age here, but Brian Kent, when I was growing up, him and Oliver Pacegape were 2 of my great heroes. So Brian Kent did Play School, Play Away, Trumpton, all of those programs, and he died this week at 83 of Parkinson's disease. Other famous people, John Betjeman, for those who are slightly older, the poet laureate, Muhammad Ali, who died last year with it, Michael J. Fox, who's got it, who set up a foundation, the Pope before last, and then if you're really interested in Parkinson's, Andrew Lees, who's a great neurologist in London, wrote a fantastic article on Ray Kennedy, which will only appeal to certain people in this audience. So Ray Kennedy was a footballer for Arsenal, Liverpool and England, and what Andrew Lees did was he went through all of the match of the days over the last 10 years of Ray Kennedy's career to try and plot when you first got Parkinson's disease. So this is a common disorder. Many famous people have had it. Average age to get it is 70, and we did a number of studies, a study a number of years ago, in which we collected everyone with Parkinson's in Cambridgeshire, and every 3 to 4 days, a new case of Parkinson's is diagnosed within the county. So by Monday, there'll be another case of Parkinson's disease within this county. And it's pathologically defined by this loss of dopamine cells. So this is the bottom of the brain, the stem of the brain. This is where your eyes are. This is the back of the brain. And at the top of this stem of the brain, the thing called the midbrain, you have these pigmented nerve cells, of which you have 500,000 on each side. And they contain dopamine, and they project up into this structure here called the striatum. And when you've lost 250,000 cells on each side, you get Parkinson's disease. So, in essence, to get Parkinson's, to present to your doctor, you need to lose, or you will have lost, about 400,000 cells and about 100 billion in your brain. So, it's a relatively small population, and that has some attractions because being a focal pathology and a very small number of cells, you can actually try and treat it and repair that particular bit of the brain. And we know that trying to repair that bit of the brain will work well because when we give people dopamine drugs, they do very well. But they do run into problems with time because the drugs stimulate things in the brain in a non-physiological way, and they stimulate the whole brain rather than just the bit you want. So essentially, there are 2 ways in which we can fundamentally try and repair that network in Parkinson's disease. One is by giving growth factors to stimulate those cells to survive and create fibres. And the second is to just replace the dopamine cells that you've lost as part of the disease process. So let's think about how we can do that with growth factors. So how can we use the growth factors to stimulate, I should say, the remaining dopamine system to grow and survive? Well, here's a brain. So how could we put the growth factor in? Well, the sort of, if you're a neurosurgeon, the obvious place to go is where there's a hole. So the first place that people thought to put it was into the natural cavities of the brain, into the ventricles. So you can deliver it directly into the fluid-filled cavities of the brain. So that's one way, and that's obviously when people put shunts in patients with swollen hydrocephalus, that's what they do. So that's one approach. The second would be to take the growth factor that you want and directly infuse it into the brain. So essentially you put a little catheter into the striatum where dopamine works, which is where that red blob is, and then you just infuse your growth factor through a pump directly into the brain. The third is to say, well, that's all a bit technical and it's rather cumbersome. Couldn't we just use some system by which to deliver the growth factor, not as a continuous infusion, but as a one-off hit? So we make a gene, we have a gene therapy, we get a virus, put in that growth factor, and then we just inject the gene, releases the growth factor, and that does the job. So that's the idea, and all of these have been done with respect to Parkinson's disease and trying to repair the brain. So we've got ways in which we can put the growth factor in. The question is, well, what do you want to put in? So what's the best fertiliser for dopamine cells? Well, no one's quite sure, but the one which people really like is this factor called glial cell line-derived neurotrophic factor, which was discovered in 1993. And this is a growth factor which not only stimulates dopamine cells, it stimulates other cells in the brain, but it's particularly good at stimulating the dopamine cells. So what's happened with GGNF as a way of trying to treat Parkinson's disease? Well, the first thing to say, which I'm not going to talk about, is when they injected it into the ventricles, which is where they started 20 years ago, what happened was it went into the ventricle, it went round the ventricles, it came out of the ventricle and disappeared, and never got into the brain. So the outcome of that trial was it didn't work. And this is a sort of recurring theme. If you don't quite know what you're doing and you don't do it right, it's quite easy to come up with a negative result. And the trouble with the negative results, people think that's the end result, rather than it's just something you've learned on the way. So people can make premature conclusions about this. But down in Bristol and in Kentucky, 2 groups said, I don't think this is the right way to do it. What they thought was it was better to put a catheter into the brain itself and then infuse GGNF directly into the brain to stimulate the remaining dopamine fibres to grow and benefit the patient as a result of this. So this trial was done about 15 years ago, so that's the direct brain infusion of GDNF in Parkinson's disease. And although you can't really see that, the critical thing is that all the graphs go down, and that is an improvement. So this is over a 12-month period when patients in Bristol were directly infused growth factor into their brain. Over time, their Parkinson's disease got better when they were assessed clinically. Now, that's a great start. The question is, well, did they get better because they had more dopamine in their brain? And the answer was, well, yes, because this is a scan called a PET scan where they look at a thing called F-DOPA, which is a sign of dopamine terminals, and they demonstrated that within the area where they were infusing it, and even back where the cells come from, there was an increase in signal. So the patients got better, their scan got better, they had more dopamine in their brain, and then one of the patients sadly died 18 months after this had all been started. They got a clot to the lung and died, and at post-mortem, at the site where the growth factor was being infused, there was sprouting of the dopamine terminals. So this demonstrated patients could get better, the scan could get better. That correlated with an improvement on the post-mortem in one patient, and furthermore that the improvement seemed sustained. So this was done on about 15 patients in 2 centres, and as a result of that, everyone thought they knew how to do this. So a few years later, in about 12 years ago now, they did what they called a double-blind placebo-controlled trial where they took 34 patients with pod disease, half had growth factor infused, half had salt solution. At 6 months, they said, what's the difference? No difference at all. End of story. So that was it. That was the end of GDNF. GDNF was owned by a company. The company decided to pull the plug on it. It's a bit of a problem because these patients were still having their infusions down in Bristol because they said it was working. But once the company pulled the plug, they then lost their therapy, which they said was helping. So this caused a huge punch-up in the world because patients said, who actually has the right to decide on treatment? I am the patient, and I've got better, so I should have it. The physician said, well, I entered the patient, so I should have the right to give the patient the treatment if I think it's helping. And the company would say, yeah, but you haven't invested 150 million quid in this. We have. It's got no future. We're pulling the plug. So this actually caused huge sort of repercussions about how we think about these types of therapies. The consequence, however, of all of this was that Steve Gill, who's the neurosurgeon down in Bristol, who looks a bit like Joe 90, and he's absolutely determined to get things, fought the case and eventually got GDNF back into the clinic. And so he has just completed a trial down in Bristol. The last patient was treated last year. And this is what they've done here. They've developed this amazing delivery system. So this is like something out of the Matrix. So these are essentially patients who have this port put into their skull just behind their ear with a cap on it. And then they go in, I can't remember, every 4 weeks to have infusions. So they have this in all the time. And this basically has inside of it a whole series of catheters that run into the brain where dopamine works. Every month they pop up to the hospital, they get this device attached, connected to this, and then they get their infusions of either GDNF or salt solution, because it's a placebo-controlled trial, into their brain. Now, this hasn't yet published, so the trial's finished. But what we know is it's worked as much as it's been very safe, and we will soon find the results out as to whether this is a useful therapy. So trying to repair the brain by putting fertilizer directly in the brain is still there. We still don't know whether it works. However, back when the GDNF study failed, the original one, there was a group of patients, a group of researchers who said, but we want to use gene therapy. We don't want to use these infusions. We don't like these infusions. They're cumbersome, they're difficult, they're going to create complications. Can't we use a gene therapy? So they did a whole series of experiments in monkeys and rats and showed that this worked very well. GDNF delivered the gene therapy, but unfortunately they couldn't use GDNF with a gene therapy because they didn't own GDNF. So the molecule itself, not the drug, but the molecule itself was owned by the company. So they then had to make something that was like GDNF, which is this thing called nurturing. So what they did was that they made a gene therapy. So this is a virus, adeno-associated virus serotype 2. They attached nurturing to it, did a whole series of preclinical studies, and then did a study in patients. And what they showed here, so the principle's the same: you inject the gene, it reduces the growth factor, it should promote sprouting and recovery in the brain. What they found was, when they either used sham surgery, so pretending to give the patient something, versus actually, there was no difference at a year, but there was a difference at 18 months. So fueled by that data point, they went on and did another study where they gave more in 2 sites and found it didn't work. So I was a bit disappointed. And so the question is, well, why didn't it work? Does it work because this is a stupid idea and it's just a flawed logic? Or are there other reasons for it? Well, I would say there were 2 main reasons why this failed. The first was, what they did was they were treating patients, and this is also true of the Bristol study which is just completed, using patients at this stage of the disease, whereas in point of fact they'd have been much better going right at the beginning. Now, why is that? Well, if you look at how many dopamine nerve fibres you have when you're infusing your fertiliser, at 1 year you have lots, at 3 years you have quite a lot, by 5 years you've got almost none, and by 15 years there's nothing. So if you're going to put fertiliser on your lawn, you really need grass seed there for it to work. So if you've got the best fertiliser ever, there's nothing there to grow, it ain't going to grow. So one of the problems, I think, was that they were giving it or infusing it into science when there's nothing left to regenerate. The second problem is that actually the amount they gave was the wrong dose and the wrong volume. So if you actually look at the amount of brain that received the growth factor, these are patients who died from unrelated causes after the study with the gene therapy, only a tiny bit of the brain actually received the active drug because they didn't give enough to fill it all up. So they gave to the wrong stage in the wrong dose, and the other thing was they probably gave the wrong type of virus because that virus is very sticky and doesn't diffuse through the brain. So armed with that information, a new trial is now ongoing in the States to try and address that issue using GGNet. So growth factors as a way of repairing the brain, as I say, have had a somewhat checkered history, but this is a strategy for repairing the brain. And you could apply it to any disease. So anything where there's a focal problem, I want to try and repair it, put some fertilizer in it, try and get that system to regenerate and grow. So that's one way of tackling it. The second is actually just saying, well, I'm going to replace the cells. Let's not bother trying to recover the system that's there. Let's just go in and replace what's missing. So that sounds quite interesting, sounds quite exciting. So can we do that? Well, this is something that you can do and has been tried with almost anything. So I'm going to take you through a story now about how this can work really well and how it can go disastrously wrong. So this is a big problem in the world at the moment, which I'll come on to, which is stem cell tourism, which is where everything can come slightly unraveled. But the essential thing here is I say, well, Parkinson's, you lose 250,000 cells on each side of the brain. I need to find some dopamine cells, and I need to put them in the brain. That's what I need to do. So where can I find myself some dopamine cells? Well, the body has lots of dopamine cells, but they have in different sites. So you have them in your adrenal medulla, which is in your adrenal gland that produces adrenaline, which sits next to your kidney. So that might be a site, and that was very much in vogue in the 1980s. The carotid body, which sits up here next to the carotid artery, which senses oxygen in the blood, that has lots of dopamine cells. People have pulled that out and shoved it in the head. You have little sympathetic neurons here, produce a little bit of dopamine, they take that out and shove it in the head. So people have done all of this. The one thing you can tell, or you can say with confidence, is it never works in animal models, so it's very unlikely to work in people, and that is the case. So all of those, great idea, doesn't work. So where are we going to get dopamine cells from now to repair the system? Well, it's a bit of a complicated figure, but there are essentially 3 main areas. One is you can say, why don't we collect the dopamine cells from the developing fetus? So where the dopamine cells normally develop in the midbrain of fetuses, can we get those? And that obviously involves going to termination of pregnancies and abortions. So could we use those cells? And I'll come on and talk about that. An alternative is to say, couldn't we get dopamine cells or make them from embryonic stem cells? Well, embryonic stem cells are the cells that we all once were. So at some point in our life, when the egg is fertilised, it starts to divide, and that is an embryonic stem cell. So an embryonic stem cell gives rise to every cell in our body, so you can collect the spare embryos from IVF programs, grow the cells up from that, and you make embryonic stem cell lines. So could we use those cells, turn them into dopamine cells, and put them in the brain? And then the third is this new technology for which the Shinya Yamanaka and Kyoto won the Nobel Prize in 2012, which was this discovery that you could take adult cells, so you take cells from the skin, from the blood, you take adult cells, and you then program them so they turn into embryonic stem cells. So you take the cell, adult cell, reprogram it back to its very origin, and then flip it into a dopamine cell. And those are called induced pluripotent stem cells. So can we do that? So those are your three main options. And how far have we got with using those in the clinic? So fetal dopamine cells, these are the ones I'm going to talk about to begin with. So the idea here is you collect the dopamine cells from the aborted fetus big brain, turn them into a sort of soup, and then inject them into the brain of people with Parkinson's. And this has been going on for about 30 years, and when it works, it can work very well. Oh, you can't see anything. I've got a brilliant picture here. Well,
at the back.
Anyway, I have to show you the graphical version of this. Maybe you can't see the video, because essentially what it shows is it shows a man who's had Parkinson's disease for 30 years, he's had a transplant of fetal dopamine cells for 20 years, and he looks entirely normal. And if you look at his actual motor scores, his scores, when you actually assess him, are less than when he presented a quarter of a century earlier. And if you look at the dopamine levels in his brain on imaging, they are entirely normal. So some patients who've had fetal dopamine cells transplanted in the brain have a clinical response that can last for more than a quarter of a century. And that's pretty spectacular, because you know where Parkinson's normally goes, it just gets worse. So we know that this approach can have long-term clinical benefits. This was a paper from last year from my colleagues in Sweden. This brown smudge here and all these brown dots are a transplant 25 years after it was put into the Parkinsonian brain. So 25 years after the cells were grafted in, they're sitting there, they look quite happy, they connected with the brain, so they survive long term. So they work long term, they survive long term, they improve aspects of all aspects of Parkinson's disease. And the other thing they do in this rather nice study is when you stimulate the transplant with amphetamine, this is just experimental, it's not normal treatment for Parkinson's, I should say, but when you stimulate the transplant with amphetamine, it releases dopamine just like the normal dopamine cell. So it releases it in a physiological way. So this whole process seems to work very well. The problem was it didn't work in everybody, and as with growth factors, it was very much taken up by our colleagues on the other side of the Atlantic. It was subject to double-blind placebo-controlled trials when they didn't know what they were doing. It produced negative results. The person in the White House had changed, the whole political landscape changed. So this whole therapy then fell into disrepute if it didn't work. But I demonstrated, at least I demonstrated myself on the video, that it works extremely well. We went back and analysed the data, and that's led to a new study which we're currently doing, where we've grafted 10 patients in the last 2 years using fetal dopamine cells implanted into their brain to try and make them better. Now the problem with fetal dopamine cells is you have to use aborted fetuses, so that brings with it big ethical problems. You need several in order to treat one patient, so in the time it's taken us to graft 10 patients, we've had 72 surgeries at Addenbrooke's, which we've not been able to use because we've not had enough tissue. So this is a big logistical problem, and so that is not the way forward. We've got to find a better source of cells, and what sorts of cells can we use? So coming back to our stem cells, well, what about iPS? So this is the idea that you take some cells, an adult cell, turn it into a new stem cell, and then flip that into a dopamine cell, reprogramming your adult cells. Now this has two attractions. One is you don't have all the problems, the ethical problems of fetal tissue. You don't have all the ethical problems of using embryos, because you have to destroy the embryo to make your embryonic stem cell line. And people love the idea that you can treat yourself. So I could take Ed, take a bit of his skin cell, flip it into an iPS cell, flip it into a dopamine cell, and he's got Parkinson's, plug it in his head. You could take these cells, turn them into iPS cells, turn them into beta insulin-producing islet cells, put them into his, under his skin, treat his diabetes. So it has a great deal of attraction for this reason. So you could use it for autologous grafting, and it's ethically more neutral. The problems with it, as it stands at the moment, it's only been around for 10 years. So you're engineering cells, so I don't quite know what that means for their safety in the long term. If I wanted to treat Ed with his iPS cells to treat Parkinson's disease, as it currently stands, to do that program to treat him would cost me around £3 million. So it's a bit expensive to treat everyone in that way. And then the other problem is, of course, if I use Ed's cells and Ed's got Parkinson's disease, I'm now turning his cells into dopamine cells to put them back in his brain. But he's got Parkinson's, so what's to stop my cells that I put back developing Parkinson's disease? So whilst it's attractive, the autologous, there are some issues with it. But nevertheless, this has gone quite a long way pre-clinically. So this is big in Japan because that's where they discovered it. So they've now done extensive monkey studies to demonstrate you can use both monkey and human iPS cells to treat Parkinson's disease in monkeys. They've also developed this in other areas, and in fact, on the 12th of September in 2014, they actually treated a patient with a different disease where they had an age-related degeneration at the back of the eye. They treated that patient with their own iPS-derived retinal cells for repairing the eye. So iPS treatment for patients with diseases has happened. And that patient stabilised as a result of that therapy. They were going to do a second patient. They didn't for two reasons. One is they were worried about the safety of the cells, some genetic abnormalities. And secondly, they realised it was going to cost too much to take this on as a therapeutic. So iPS cells are possible, but there are issues. How about embryonic stem cells? Where have we got to? So this is the idea that you take spare embryos and you turn them into dopamine cells. Well, this has already gone to clinical trials, as I'll show you. Very easy to do it. Ethical problems, though, because you're having to destroy embryos.